sorting? Oh, get me my mic. I don't think I want to. I mean, I need
from like those random
maybe.
you have a Goldman Sachs account. Goldman Sachs. Okay, what am I going
You folks might also go upstairs and you want me to might also view the German class and just check how it's working in Toronto. You ready? Okay. All right, everyone. Good morning. Good morning. Morning. What's going on? Nothing there? Okay, we'll debug it. Okay, good morning. We have a quick guest announcement. Take it away.
Hi everyone, my name is Amy and I'm a coordinator for Women in Computer Science at Brown. So we're dedicated to promoting diversity and inclusion across gender identity in the CS department. We have a mentorship program where you can get paired up with an older CS student and kind of have coffee chats, go get meals and like learn about more of the department. Our upcoming event is this Friday, September 14th at 4 to 5 in the CIT library, which is going to be on the 4th floor. There's going to be food, Chipotle, and also we'll have an intersequence panel where people talk about their experiences and how they choose their classes. We also have a lot of different events throughout the school year and we like partner up with companies, so make sure that you sign up to our listserv through the Google form, which is that link. So if you go to tinyurl/brownwix, you can sign up there. And yeah, that's all. Have a good class.
Thank you for coming. Wix does really good work in the department, and so I really you should go check it out and go attend their meetings and get involved. Thank you.
Thank you.
Okay, so today I want to focus on one topic. This is going to be an interesting lecture because this is the moment when those of you who did high school computer science are going to have all sorts of interesting opinions, and those of you who didn't will have no idea what's going on. And at the end of the day, it'll turn out maybe the second group will come out a little bit further ahead. Okay? So pay attention to the question you're being asked rather than the question you think you want to answer. Okay? All right. So let's start. I need to let you get this out of your system. So let me ask the question, okay? We're going to talk today about sorting, okay, which is the idea of putting things into order. And just for simplicity, because there's going to be enough moving parts today, let's just focus on sorting lists of numbers into ascending order. Does that make sense? List of numbers in ascending order, right? We've got a well-defined problem. We don't have to worry about strings. We don't have to worry about descending order or anything else. Sorting list of numbers in ascending order. It'll turn out, shockingly enough, that's going to take all of today's class. Yeah, how's that? Okay, so what's the most natural sorting algorithm? Yell it out. Yeah, everyone's got an opinion. Why? Silence. Okay, good. So let's do this. We're going to try to figure out how to sort a list of numbers, okay, using only what we know so far, right? Remember, 19 is not about how much high school computer science do you know that you can show off. How much have you actually learned this semester? That's what I want to test, right? So we're going to try to sort a list of numbers using just what you know so far, okay? You're going to turn to your neighbor, introduce yourself, tell them your name. Even if you've told them before, they may have forgotten, so tell them your name again, okay? And start working together. Let's go. Is that okay? Now it's on. This is a problem. Okay, what do we have so far? In 5, 4, 3, 2, 1, and we're back. What do we have so far? Do we have, yeah?
We talked about using fold to do insertion sort.
We talked about fold. I don't know what insertion sort is, so I have no idea what that means. Okay, next. Yeah,
We talked about using like a maximum function and
maximum function. Yeah, back there. It's maximum function, maximum function. Anyone write an example down? No. Yeah? Give me some examples. Go.
3, 5, 2, 7, 5, 1, 8, 2 to whatever that is sorted.
3, 5, 8. I have to do all the work. 3, 5, 8, 7, what? 1?
3, 5, 2 actually, sorry.
Okay, that's good enough. So what does this turn into? What does this turn into?
1, 3, 5, 7, 8.
1, 3, 5, 7, 8. Okay, any other examples? Yeah.
1, 3, 5, 4, 2
1, 3, 5, 4, 2.
goes to 1, 2, 3, 4, 5.
Okay. No getting past that. Another one, another one, another one, another one, another one. Yeah, go ahead.
3, 3, 3.
Ah, okay, very good, very good. Okay, 3, 3, 3, and in the same order, or? Sorry. sorry. Okay, another one, yes. Sorry, what's that? Is this charged up now?
Yep.
Okay, okay. Give me a moment, please. Never mind this. Okay, go ahead, sorry.
Empty list.
Ooh, nice. Goes to?
Empty list.
Empty list. Okay. Any other interesting examples? Yeah.
Negative number. 1, yeah, 1, 0,
raise your
negative
hand.
1 goes to negative 1, 0, 1.
What was that again?
1, 0, negative 1 goes to negative
1, 0, negative 1 goes to?
Negative 1, 0, 1.
Negative 1, 0, 1. Any other interesting examples? Yeah.
1, 2, 3 is 1, 2, 3.
1, 2, oh, okay. 1, 2, 3 is 1, 2, 3. Okay. What is the point of these examples? What is interesting about this example?
It's just a general case of how it we use.
It's just a, a sufficiently already sorted list, right? What's the point of this? Similar. What's the point of this?
The same.
if you have multiple elements.
Yeah, there's actually two different things going on here, right? But the critical thing is if you have multiple elements, make sure you don't lose any of them, right? What's the point of this? Make sure you get your base cases right. What's the point of this?
Negative and 0.
Right? Make sure that you actually put negative numbers in the right place. And the point of this? If it's already sorted, make sure that you don't screw anything up, right? The Hippocratic principle of sorting. Okay, good. How do we go about writing code to solve this problem? So what many of you are doing is relying on your prior knowledge, which is always very useful, unless you happen to not have prior knowledge, right? And believe it or not, we're going to do things in this course that you haven't already done in high school. Hard to believe? Okay, well, let's consider that a challenge then. Okay, so what do you do when you can't just rely on what you already did before? That's what we want to do. Okay. Okay. That's a bit loud, isn't it? Audio mixer. Okay, is that better? Yeah, that's definitely better. Okay, good. So you remember what we talked about this summer was let's look at our template step. Remember the templating step, right? So what data definition are we working with? Okay. So we have a data, a list of numbers is what? How many kinds of lists of numbers are there?
2.
What are they?
Empty.
Okay, so you have an empty and you have a link of a thing that's a number, right? And a rest which is a list of numbers, right? Okay, So that's our data definition, right? Now in this case, obviously this is built into the language, so you don't have to write it afresh. But you're going to be writing new data definitions from scratch, right? So I want to make sure we understand how to work with this. Okay. What does the template for this look like? I'd like you to work with your partners. I'm going to give you about a minute or two to come up with a template for a list of numbers. Go. Wait for everyone to come together and you can ask the question again. Not even remotely. Okay, in 5, 4, 3, 2, 1, we're back. Half of you are horribly confused, right? Okay, why? Why are you confused? Can you ask a question that the others might also have that we can share, and we can try to figure out why there might be any confusion here? You have a question?
Yes. What is a template?
What is a template? How'd you get through placement? No, I'm kidding. Okay, sorry. So, what is a template? Anyone have an idea what, I mean, I know it's the step you all skipped, right? So that's why I'm doing this here. Why? What was the purpose of the templating step? There's actually a very, very important reason why it exists. Do you have a suggestion?
Oh, it's to handle like every case.
Okay, it's to handle all the case in the data. Other answers?
Yeah, almost all functions on a list of numbers will look the same.
All functions on a list of numbers likely to look the same, and it's trying to get that commonality. Another answer?
Just kind of mapping out like the plan of what you're going to do before you implement it.
It's a mapping of a plan of what you're going to do. Other answers? Any other answers? Yeah.
So you account for all cases?
Making sure you account for all the cases. Other answers? I'm going to give you, so every one of these answers is totally legit. I'm going to give you a slightly different version of the answer, okay? Which is, what it is an attempt, and so you're going to notice that I'm going to pick on elements of each of these answers. It's an attempt to extract as much code as we can out of the data definition even before we know what problem we're trying to solve. Okay? So it turns out there's a whole bunch of things we can learn just from the data definition that give us suggestions about how to go about solving the problem. And we could, in principle, do this without even knowing what problem we're trying to solve. So let's think about what a template looks like for a function over a list of numbers. So it's a function, and it's going to be a function for a list of numbers. Okay? It's going to take a L, which is a list of numbers. Okay, what does it produce? We don't know. I haven't told you which function it is. It's just all we know is that it consumes a list of numbers. So you think there's not a thing we could do. What could we possibly write? Well, that's what we're going to find out. Okay? Well, what do we know just from the data? What do we know? What is the thing we know?
There are two cases for what L would be.
So we know that L is a list of numbers, even more simply, right? We know that L is a list of numbers, and therefore,
There are two cases
how could you possibly have known that?
because we defined it.
You just did something really important. You pointed. Can everyone point? Okay, this is the robot hand. Control the robot hand. Takes 4 instructions, up, down, left, and right. Left.
Stop right there. Stop is not an instruction.
Stop, 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 stop. Oh, yeah, I'll give you that one. Okay, so right there, okay, well played. So right there, we've got two cases, and that's what tells us that we are quite likely to want to have two cases here. And what are the two cases? It's an empty, and it's a link of a first and a rest. Okay? Now, question to ask yourself. Have we exhausted the information available to us in the data definition? Have we run out of information in the data definition?
No, first is a number.
No? No.
Yeah.
Okay, let's do this case by case. In the empty case, do we have any more information at all?
No.
You sure? How can you be so sure? For people so young, such certainty is amazing. Because it's empty, there's no more information. Of course you're right. Okay? So we don't have any more information based on the data definition. Based on the structure of the data, we've exhausted the information. Okay? What about in the link case? Do we have any more information?
Yes.
What information do we have? What is the most basic thing we know? We know something about F and we know something about R, right? In fact, we know that F and R exist. We've already encoded that over here. Okay? What do we know about F? Okay, we know that this is a number. And what is R? How do you know that? Thank you! Point! 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 I want everyone to point. And I want all of you to point in the same place too. That would be even better. Okay? So, we know that R is a list of numbers, right? If we want to write a function over a list of numbers, is there anything that might help us with R? Chances are it is something that fits the template of a function for a list of numbers. Yes?
You could call FLON on R.
Right, so what we would really like to be able to do, so if we had the syntax, I would parallel that arrow over there, right? I would say that's the same kind of thing, okay? Now, there's a subtlety here. FLON, is that one function?
Yeah.
It's a type of.
Yeah, actually it stands for an infinite number of functions, right? We don't know how many functions are. There could be any number of functions, and there are many, many, many functions, like you said, right, that match this structure, right? We don't know which particular function it's going to be. So we've done the thing that several of you said. We've exhausted the cases. We've made sure that we didn't miss any cases. But this really is saying some function over lists of numbers would be useful to you, but hint, hint, maybe it's even the same one. Right? It's not that it can't be the same one. It's not that it must be the same one. Okay? So what we are doing is we're extracting code for free from the data structure, from the data definition. Do we know anything more about F?
No.
Where should you be checking?
Data definition.
Do we know anything more about about R? Sorry.
No.
All we know is this information. Now we're done. Okay? We have generated a whole bunch of code for free without even, this is very important, thinking. We got all this code for free without thinking. Okay? It just fell out from the structure of the data independent of the problem we're trying to solve. That's very critical. Independent of the problem we're trying to solve. Okay? And the same method is something that will also apply in other languages. So it's not a pirate specific thing or a racket specific thing. The same idea carries over if you do object-oriented programming. The same sort of idea that what you're trying to do is you're trying to drive the structure of the program from the structure of the data. This is the central idea to object-oriented programming. You drive the structure of the program from the structure of the data. There are slightly different language mechanisms in object-oriented languages, slightly different language mechanisms over here, but it's the same idea. Okay? Think hard about your data structure, use it to drive forward a proposed structure for your program. Okay? Good. Any questions about this? Yes?
Yeah. Does that include the case where like you don't have to do something on F or R after link. So if you're
So this is only giving you a suggestion, right? Supposing I gave you, for example, the actual problem. I'm just giving you a problem, right? So let's say I gave you a problem that said, given a list of numbers, produce 3. It's not a very interesting function, okay? I'll grant that, okay? Do you need to do a cases? You don't need that, right? Supposing I asked you to compute the length of the list, do you need to worry about what is the first element? This becomes 1 essentially, right? All the first elements become 1 essentially, right? So, depending on the actual function, you may not need some of these pieces or even any of these pieces, right? It's telling you what's available. It's giving you an inventory of parts. These are the parts you have that you can use to assemble your solution, okay? So far so good? Good. So, everyone with me? That's our template step. We've got a template. Now, next step is, let's say that the actual function I asked you to write is sort. So, what I want you to do is, using this template, start writing a sort function. Go.
Yeah, sure. We can do it. MD's gonna do it. If it's doing an do a local function. Like just make a local function that's added to that place. Okay, if it's less than it, like go to yeah.
there is
All right, in 5, in 4, 3, 2, 1, and we're back. Okay, so I've got myself most of the template here. Oops, I didn't copy the whole thing. So I've got F, and I've got sort of R. Okay, so let's start filling in the code. Okay, in the empty case, what is the answer? How do we know this? Because we already thought this through. We wrote an example, right? And maybe you even got an exemplar instance that you could test it against, or maybe not, right? But you got an example, you've thought this through already. So we don't need to think about it anymore. Okay? Okay, now let's look at the other case. Okay? What are the pieces we have? Let's inventory our pieces. What parts do we have to work with? How many things do we have to work with? Two things. What are they? F, which is what? It's a number. And what's the other piece? What is the other piece? It is sort of R. Right? Now, we purposely skipped a step. Purposely skipped 2 steps. Okay? We never filled in our contract. What's our contract? What is the type of sort? What does it produce?
Oh,
Somebody had a hand up there? Yeah.
a list of numbers is
It's a list of, so it's a lawn, but in fact it's not just any old lawn, it's actually a lawn that is in ascending order, right? And right now I don't have a way of writing that. We can talk about that if we have time in class, okay? So what does sort of R give me? What is the purpose of sort? The purpose of sort is what? To always talk in terms of consumes and produces. Consumes a list of numbers, potentially unordered list of numbers, right? Potentially not, and produces a sorted list of numbers where sorted is assumed to be in ascending order. Okay? So what does sort of R do? It consumes the rest of the list of numbers and produces the sorted rest of the list of numbers. Right? Good? I want you to talk this through because we're going to be doing more and more examples like this in class where it's going to, and for homework in particular, where it's going to be helpful for you to follow this discipline. It'll make your programming lives much easier. Okay? So, this produces the sorted rest of the list of numbers. And what do we do with this F? Do we link it? That's what we always do, right? We have a value and we have the rest of the list and we just link the two, right? So, link F onto sort of R. Good? No. Why not? What would it violate? What would it violate? Point to the board. Where does it violate something on the board? What on the board tells you that something's been violated? Where are you pointing? Up, down, left, right? Yell, man. Up, right.
Yeah.
Stop there. Yeah. We wanted that to say a sorted list of numbers, right? Supposing I had said this, right? That's what I really wanted to say. So our type language is not powerful enough to express what we want, okay? Supposing it were, then we'd be clearly in violation because we don't have a guarantee. We are still producing a list of numbers. We don't have a guarantee that F is in the right place. Okay? Is there an atomic instruction that's going to solve the problem for us? Maybe it's not link. Maybe it's reverse link or something like that. Anyone think of an atomic instruction? Not obvious, right? So we'll give ourselves the freedom to write a helper function. We want to insert F into the right place. Maybe it's the beginning, maybe it's the end, maybe it's somewhere in the middle. Okay? So yeah, we're doing insertion sort. Okay. So we're going to insert F into the right place in this list. Okay? Why did I use different colors? Is it because my marker was out? Why did I use different colors?
Because inserts a helper function is sort of what
No, but there's like lots more than that, right? That's all true. That's absolutely true. But there's more than that, yeah.
Everything is not the templates in different color.
I'm showing you how much code you got for free from the template. Right? And if you actually got your template right and you spent a minute looking at it syntactically, you can avoid a whole bunch of syntax errors, you can avoid a whole bunch of problems, right? You will just get it for free. You can copy that template as I have over here. And you can use it multiple times to write multiple functions. Okay? And you'll have homeworks where this will turn out to be a useful, smart thing to do. Okay? Good. So now, we need to still write insert. We're not done yet, right? Okay, go do insert. Go.
And then it's a number. A number is I mean, oh,
Yeah,
yeah.
the same template that's gonna be like the big same template to the method function.
Oh, wait, maybe like empty, it's gonna be linked. Yeah, the number and then the student.
In 5, in 4, 3, 2, 1. And we're back. Back. Okay, let's first make sure that we have the template right over here. Are we okay with this template here? No. Why not? You claiming I got the template wrong?
Well, for this function,
I guess you are. Okay, yeah.
Yeah.
What's the problem?
you need to insert a number for this.
Yeah, so our contract isn't even right, okay? So we have to work on the contract. What do we need to do? We need to say that we actually want 2 parameters, right? So I want, I'm going to play this dance of markers here. I want, and this is now called insert, okay? And I want a n, which is a number, and I want a L, which is a list of numbers, okay? And what does it produce? Think hard. What does it produce? Does it produce? Anyone on this side of the room? Anyone? Sorted list of numbers? Okay. Okay. All right, we'll come back to this. We'll come back to this. We'll come back to this. Ah, wrong color, wrong color, sure. Wrong color. Okay. We'll get back to that. Let's just write list of numbers for now, okay? Okay. Anyone have any thoughts about what to do in the empty case? Yeah.
You would return like a
Empty,
which
right?
is the number.
Okay. So empty.
No.
Why not? It is indeed a list of numbers.
You need to return the new number.
We've lost our number, right? So we need to instead return. We could write it this way, right? Or link of n onto empty. Okay. So notice that the answer is not always empty. You will make this mistake. Sooner or later, you're guaranteed to make this mistake. Okay. The answer is not always empty. Okay. Now, what assets do we have over here? Do we have more assets than what we've written down?
Yeah.
What other assets do we have?
We have n.
We have n. We've also got n, right? And that is a number. In fact, we're sort of getting a hint. We've got n and f, and then we've got insert, right, over here. So we actually also have to deal with that, right? We have to put an n in there somewhere, right? Probably it's the same n. Sometimes it won't be the same n, depends on the problem. But in this case, it's going to be the same n because it's the same number we're trying to insert. Okay, so what are we going to have to do? We're going to have to compare. Yeah.
Could we do like an example or two because I'm not.
Oh, no. You're way too mature for that. No. Okay, so it would actually be a very good idea to do an example. Okay, so insert. Okay, so who wants to give me an example? Give me a good example. You got a good example? Somebody got a good example? You have a good example? Good example.
Insert 2 into the list 3, 4, 5.
2 into 3, 4, 5 gives me
2, 3, 4, 5.
2, 3, 4, 5. Okay, somebody else want to give me a good example? Do you have a good example?
Yeah.
Good.
So 1 into 0, 1, 1, 2.
Oh, 0, 1, 1, 2. What's that produce?
0, 1, 1, 1, 2.
0, 1, 1, 1, 2. Okay. Another example. Example, go.
-1 into -2, 0, 3.
Okay, what's that produce?
-2, -1, 0, 3.
Okay. Another example.
I'm not sure what this would go to, but 2 and then into 5, 4, 3.
2, oh, I love it. 2 into 5, 4, 3.
Not sure what that's supposed to produce.
hold on to that. Back there. Did you have your hand up? Yeah.
3 into
Oh, 3, excellent. Thank you. 3 into empty. Always forget the base cases. Okay, so what's that?
That's just
The list 3. Okay, good. Okay, great. Another example, yeah.
4 into 1, 2, 3.
4 into 1, 2, 3. Isn't that, oh, we don't have that, right? 4 into 1, 2, 3. 1, 2, 3, 4. Now, there's a dead silence over here. I want to fill this gap over here. What do we do with this gap? What do we do with this gap? Yeah.
I mean, I don't feel like that should be an example.
You don't feel like that should be an example? That is a list of numbers, sir.
Well, maybe we should clarify our...
Oh, maybe we should clarify.
Because I think the second parameter should be a sorted list.
The expectation of insert is that's only being called on sorted lists of numbers. And we're satisfying that expectation here by only calling it on sorted lists of numbers because it's not clear what it means to insert something into the right order when it's not ordered, right? I mean, well, okay, so, you know, this is ordered but in the wrong way. It's not ordered in the way we're talking about, right? So this is a non-example, okay? It doesn't match our contract, our implicit contract. And when you wrote out all the steps, which you will do, right, you would have said something about it being sorted. Okay, so now, who asked for examples? Good. Useful?
Yes.
Good exercise. Thank you. All right, so now we get even some sense of what our strategy might be, right? We can unroll these to figure out what we're going to do. We're going to, so this part I'll go through a little quickly, okay? We are going to ask whether n is less than r. And if it is, what do we do if n is less than r? Yeah, that's what we shouldn't do. Thank you. Okay. Okay. I would like to pretend I was trying to check whether you were on your toes, but I wasn't. I was just wrong. Okay. So, is n less than f? If it is less than f, what do we know? N, the thing we're trying to insert is
less than the first
smaller than all the elements in the list. Therefore, it should be the first element. How do we make it the first element? Link. Okay. And onto L or R. This is a place where I promise half of you will get it wrong in your code, and you will not discover it because you never bother to write an example. And we will get so much joy out of catching you out on it. Okay? So, are we doing the rest? N is smaller than F, which means it is smaller than all the elements, not only in the rest of the list, but in the entire list. Okay? So, we really want to do that against L. Okay? Else, what do we want to do? We want to, well, N is no longer the smallest element. What is the smallest element? I mean, there's also an n equals f case, but you know, we can gloss over that a little bit. We can just say this if you want, okay? So f is in fact the smallest element, therefore it must be the first thing in the result. Okay? So we need to link, wrong color, we need to link the first element onto, we still don't know where it goes, but is there anyone who can help us out? Insert. Okay? What are we trying to insert? N onto R. The comma should be blue, sorry. Insert that into that, and then close that. And then this whole if was introduced by the program logic, so we need to mark that in the right color. Okay? Notice a few things. We didn't use R over here, we actually used L, right? That was technically something that was available, even though we didn't write it explicitly, it was actually available to us, right? So that was there, okay? That was all reused, right? what we can see by the two colors is what is generic to list traversals versus what is domain-specific logic. It is specifically the logic of insert. In fact, it is the logic of this particular kind of sorting as opposed to maybe sorting in the opposite order, right? You might get a different thing over here. In fact, what should you really be doing? Should you be writing different sorts for each kind of order? You should pass in a function that tells you how to order elements. Okay? And you all know how to do that now, right? Really, what you should do is sort should take also a thing that says how do I compare and order elements and pass that through to insert and use that over here. That's the right way to do it. Okay? I'll let you think about that, how to generalize that. Right? So, yes, question.
Is such a thing as optional parameters in...
In Pirate, no. And I could spend hours talking to you about why not. But no, there are not. Yeah.
Is that the same thing as default parameters?
I don't know what either of those things are because they're not in Pirate. Okay, next. Other questions? Other questions? Okay, so what I want you to understand is what the templating step is buying you. Sometimes it buys you less, sometimes it buys you more, but it's still buying you the backbone of your program. You're always free to ignore the backbone, but it's giving you a suggestion about how to solve it. Okay? I would claim this is actually the natural sorting algorithm for this definition of list of numbers. What's going to be fun is in the middle of the semester or earlier in October, you're going to get a homework where we're going to propose an alternate way of defining a list of numbers. And it'll turn out there are different natural sorting algorithms depending on how you define the structure. Okay? But the point that how to design programs is trying to get you to understand is that the structure of the data will often suggest a default solution. Okay? It may not be the best solution, but sometimes it's awfully useful to have a first solution before you go looking for a better solution. Right? This is what we call structural recursion, a term that'll make more sense next class probably when I compare it against as opposed to what. Okay? But this is a recursion where what we recur on is decided by the data definition itself. Right? We sort on R, we insert on R, the data definition tells us consider the rest of the list, and that's what we use. Okay? One of the nice things about doing recursion structurally is you're guaranteed to terminate. You cannot possibly go into an infinite loop. You can, because you didn't write a template and then you end up writing the code, all of the code at once, and then you end up screwing up and used L instead of R or something like that. But as long as you write templates, you're guaranteed to terminate. It's like a proof. You don't even have to prove it. It's guaranteed that your program will terminate. It will always halt. It won't prove that it'll give you the right answer. That's up to you. But it's always going to halt because the data structure is finite and you're peeling it back in the same way that you built it up. Right? You built it up. You wrote examples that showed how it was built up. You're peeling it back in exactly the same order. And that's what guarantees that it's always going to get smaller and therefore always going to get terminated. If you run into something called induction in mathematics, proofs by induction, you are programming inductively. You have an inductive data structure and you are programming inductively. This is your inductive assumption here. You are assuming that sort of R is going to sort the list of numbers, and now you have to do one more step. You're assuming that insert is going to correctly insert and give you back something proper, and now you're doing one more step. It is exactly the same as induction in mathematics. Okay? And it works for the same reasons. All right? That's the power that you get out of the template step. I know it looks boring, I know it looks horrible, but it's a thing that I don't routinely do until I come to a complicated problem and I say, stop. Think hard about what your assets are, think hard about what the pieces are that are available, make sure you get the solution right. Okay? Two more comments. One, so we keep running into this frustration that our contracts are not quite accurate enough, right? We really wanted a sorted list of numbers here. What about here? Are we okay with that contract? No. What did we really want? We wanted to make sure we got a sorted lawn and we produced a sorted lawn. Right? Okay, it turns out there is a thing you can do in Pirate. I'm not going to ask you to do it this semester, but if you want to, you can. You can write list of number. Okay? But you can also write this extra thing. You write percentage followed by a thing in parentheses, which is a predicate, a thing that says true or false. And at runtime, that will be run against the value. So if you wrote a predicate called is sorted, so is sorted has to be a function of one argument. It consumes a list of number, and it produces a Boolean. Right? It says, yes, it is sorted, no, it's not sorted. If you write such a function and you put it in here, then at runtime, Pirate will run this predicate against the value every single time and will tell you if you ever get it wrong. Okay? So if you were to write is sorted and so let's say we actually wrote is this thing instead of sorted lawn. Okay? Let's say we wrote this everywhere. And we fed this as a test case. It would actually stop your program and say, I'm sorry, you did not pass, it's called a refinement. You did not pass the refined type. Yeah, you gave me a list of numbers, but you didn't give me an is sorted list of numbers, and therefore, I can't even let you run this function. And similarly, if your output were to produce something that's not sorted, it would halt and tell you that's an error. Okay? Okay, so this is just a linguistic quirk. It's a property, it's a thing that's in Pirate. It's not in most other programming languages, though a lot of new languages are starting to have it. So this is just a weird linguistic quirk. I'm just saying that some languages actually give you the ability to write the precise data definition that you want. Yeah?
If you were to generalize the code and have a function that compared each value, could you do that still?
Yeah, you could. You would just write a slightly different predicate. Right? So is sorted would then be a function of the comparator that you had. Right? So you would write this to actually be a function that consumes the comparator as a parameter and returns. So it would be your thing would be comparator to list of number to a list of, so it'd be a comparator of t comma t to a list of t to a Boolean. Right? And you would feed it the comparator, and that would then return you the predicate, and then you would supply the predicate. You could figure that out. Yeah. Other questions? I want to do one last thing, okay? Really quickly. We have about 2 minutes left. Let's think about a function like max of a list of number. Okay? What does max consume? What are good inputs for max? And what are bad inputs for max? Is there an input for which max doesn't even make sense? Input for which max doesn't make sense? Empty. What is the max of an empty list? There isn't a max. There isn't a min. It's not a well-defined problem. Average. We talked about this a little bit, right, with rainfall. Average doesn't make sense. So what we talked about in class was, hey, look, you're computing average and you've got to deal with the empty case. Really, the right way to think about the problem is average is only defined on a non-empty list of numbers. Right? It's just not defined on the empty list of numbers. What is the non-empty list of numbers? Well, non-empty list of numbers is either one number or it's a more of them, right? So there's one number and there's a rest, which is a what? Non-empty list of numbers. Now, think about your template step. Your template step is still going to have two cases, okay? But it's going to be one and more of them. What is the max in this case? It's whatever number you're looking at. It's that number. What's the max in this case? Well, it's the max of the rest compared against the first number, okay? And the entire problem of what do I do in that empty case disappears. There is no empty case. There's no recursive empty case. There's not even there's no example you can write. There's nothing you need to do, right? So sometimes what happens is the problem you're trying to solve is not over a domain you've already been given, but over a subdomain. And if you have a little bit of math experience, you know that sometimes the domain may be a subdomain of some other bigger domain, right? So just because we have lists as built-ins doesn't mean they're always the right representation for a problem, okay? Sometimes make a refined representation of the problem, and then you can do this kind of thing. You can either define this, or you could also have done something where you said list okay, list of whatever, percentage is not empty. Right? That's really what you mean. That's another way of doing it. If you do it this way, you get to reuse all of the stuff that's already built into Pirate, maps and filters and stuff like that. But you have to be careful that you always have to be checking for that non-emptiness. Or you just make up a new data type, right? That demonstrates the actual structure of your data. There is no way to make an empty thing in this data definition. Literally no way. You have ruled out using your data definition the possibility of making an empty thing, so you never need to talk about what the definition of the problem is on that case. Right? You can only have one or more than one. 1, 2, 3, 4, 5, everything else. Make sense? Again, that's the flow that Data Design Programs is trying to teach you. Okay? And you'll see more of that this semester. Thank you.